Hello, welcome to this lesson. In the Chemistry Tutor, we're going to talk in this lesson about what we call the kinetic molecular theory of gases. Now, in truth, from the very first lesson in this batch of lessons here in gases, I've actually taught you quite a bit about kinetic theory already. We talked about what molecules are, we talked about what pressure is, roughly what temperature is. But in the beginning, you kind of just talk in general terms about what those things are, and then we move quickly into the gas laws, Charles's law, Boyle's law, ideal gas law, and things like that. Now that we've done all of that, and we've done some stoichiometry, and we've done partial pressures, we need to circle back, and we need to come to a little more detail about the kinetic molecular theory that we mentioned briefly in the beginning. So everything that we've covered, that we're going to cover here, has been touched on in the past, but we're just going to go a little bit more detail. Now, one more thing I want to warn you before we get too deep into this is that even what I'm going to teach you here today really is not the full glory of kinetic theory, because really the math required to prove kinetic theory, it actually goes beyond the scope of a chemistry course. You know, it goes into statistical mechanics and other higher level math, because when you think about it, what you're trying to do is describe how this gas is behaving at a molecular level. And since there's billions and billions and billions of molecules in any gas of any size that we would have in a room, then it's impossible to really keep track of everybody's, every molecule's position, velocity, and how the gas is behaving. So really, when you dive into the math behind kinetic theory deeper than what we're going to go to here, you end up dealing with a lot of statistics because you've got too many particles to keep track of. So you start looking at statistically how will they behave. Okay, and that gets into some other physics and chemistry that are just beyond the scope of what we have here. So I want you to keep in mind the purpose of this section. It's not to teach you every single step along the way of how to derive this kinetic theory, okay, and the equations that come out of it. That's not the point, because to actually do that down at the level of that math, it's beyond the scope of this chemistry course. But what I do want you to understand is the concepts behind kinetic theory and fundamentally what it represents. And also, we're going to show some equations, and we'll have some interesting equations at the end, and we'll show most of the steps to get there, but mostly I want you to look at the conclusions and the equations that come out and have a general idea about where they come from, and most certainly understand how to use them. And so in this lesson, it'll just be theory. In the next lesson, we'll do some problems, and we'll kind of talk a little bit more about what kinetic theory is. So first, I have 6 bullet points I want to read to you. I don't want to write them on the board. I've talked about most of these already, but I want to kind of frame everything in terms of putting all this to you right now in one place. The first thing, and this is the kind of stuff you'll probably read in your book, as far as the introduction to what kinetic theory is. Gases are a collection of molecules whose volumes are small compared with the volume that the gas occupies. All that means is that a sphere of gas, or a collection of gas molecules, is basically such that the molecules, the size of these little bitty invisible things, is much, 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 much smaller than the volume that the gas occupies. So when we talk about gas theory, right, we're talking about zooming out from those molecules and looking at billions and billions of them and how they all behave together. And the size of those molecules are really, really small. That's all this means, okay? Number 2, molecules of a gas are in continual rapid motion. They're never motionless, except at absolute zero, 0 Kelvin, okay? But whenever at room temperature or any other temperature, they're always moving. They're always zooming around doing something. If you could see all of the molecules in front of you right now, you would see billions of them flying around all different directions, and they would be hitting each other and bouncing off of things, and it would be very chaotic, but they're incredibly tiny, so we can't see them with our naked eye. Number 3, molecules collide with each other, often with each other and with the walls of the container. So the molecules are moving in rapid motion all of the time, and they're slamming into each other. They're literally bouncing off one another constantly. And since they're inside of a vessel of some kind of container of some kind, they're constantly hitting and slamming into the walls of the container. Now, of course, you're inside of an atmosphere of gas right now. The air molecules are hitting each other. They're also hitting your skin, bouncing off, delivering energy to your skin as well. These collisions that we're talking about here, they give rise to the gas pressure. I've already told you this several times. The pressure that we measure inside of a vessel or on your skin or whatever really is just measuring the force that these molecules, billions and billions of them, are doing when they hit something. So it's like tiny little pushes, and when you add all of them up, they add up to something more than a tiny little thing. We can actually measure it. Okay. And the average kinetic energy, this is really important, the average kinetic energy of the gas molecules is determined by the gas temperature. I probably mentioned this already once before, but it's really one of the most fundamental things of kinetic theory, so I'll say it again. When we measure the temperature of a gas, what we're really doing is we're measuring the average of the energy. We call it kinetic energy because that's the energy of motion. We're actually measuring the average energy of all of those molecules that are slamming into our thermometer. If I stick a thermometer inside of a gas chamber, all of the gas molecules are going to bang into it. That's what collisions are. They're hitting it and they're delivering some energy, and they're, and maybe they increase the reading on the thermometer because of the way the thermometer is constructed. But what we're measuring is the average. Some of those gas molecules are going to have lower energy just due to random nature, and some of those gas molecules are going to have higher energy because they may be moving faster, right? But on average, that's what the temperature is measuring. So the temperature in the kinetic theory, the temperature and the average kinetic energy of this collection of gas molecules, they're proportional to one another. And we'll write that down mathematically in a second, but it's really the most central tenet of everything I'm talking about here. And the last thing is the ideal gas law, which, as you know by now, is so fundamental and so useful. The results of that law are directly predicted by the kinetic molecular theory, okay? So you got to take the big picture here and understand where this comes from. Once upon a time, nobody had electronics, nobody had computers, nobody had microscopes. They started studying gases. So what they did was measure what happens if you heat a gas up, what happens if you compress a gas, what happens if you expand a gas, what happens if you add more of a gas. And so they developed all these laws, Boyle's law, Charles's law, Avogadro's law, and they figured out how these gases behave, if they're perfect gases, right? How do they vary when you increase the temperature? How does it change the volume when this and that and the other thing happens? We talked about that. And then we learned that you can combine all of that stuff into one law called the ideal gas law, which preserves all of the behavior of those individual gas laws, but it's one nice, neat equation that we can apply to almost anything. And we've used it for several lessons now to calculate all kinds of things. But the ideal gas law really is just talking about the macroscopic details of the gas. The temperature of the gas is a macroscopic quantity. It's an average of the kinetic energy of billions and billions of gas molecules, right? The pressure that we measure, it's a macroscopic quantity. That means it's just an average measure of how much force this gas is exerting due to these collisions, right? So that's kind of aggregate behavior. The kinetic theory attempts to zoom in what is happening at the molecular level of these gas molecules, okay? And it turns out that this nice theory called kinetic molecular theory was formulated much, much later, and it turns out that the results of kinetic molecular theory agree perfectly with the results of the ideal gas law. That's why we know the kinetic molecular theory works and why it's useful and why it's correct, okay? So that's the bare bones of what kinetic molecular theory is. If you turn the lesson off now and don't learn anything else about molecular theory, kinetic theory, then everything I've said up to this point really is the take-home points, right? What we're going to do now is write some details down and guide you through just a little bit of the math. Of course, not all the gory details. It's beyond the scope of this class, but some of it, so that you can gain some appreciation for what we actually know to be true. So let me write down a fact, which I already told you in words. And I told you, I said, the temperature of a gas is really a measure of the average kinetic energy of the aggregate of all of those gas molecules. It's a macroscopic average quantity. That's what temperature is. So another way to write that in terms of math is the kinetic energy, and I put a bar over it. That means the average kinetic energy of billions and billions of gas molecules, that's what that means, is proportional, that's what that means, to the temperature that we measure. That's what this relation means. This is not an equation. This is not equals. It's proportional. So if we measure 98.6 degrees or whatever, 200 Kelvin or something, then if we measure a higher and higher temperature, that means the average kinetic energy of the gas molecules is higher and higher. As the temperature is measured to be higher, that means the average kinetic energy of the motion of the molecules is larger and larger and larger. That's what that means. That makes perfect sense. Kinetic energy means energy of motion. So higher temperature implies faster and more vigorous motion of the gas molecules. Okay? Now we can also say a few interesting things. We can recall from a physics course. So see, here we start to blur the line between physics and chemistry, because up till now we've been talking about chemistry and gases and how they behave in terms of chemistry, but now we start zooming in to molecules. We got to start talking a little bit about physics, because ultimately at the fundamental level, that's what's happening with the molecules, okay? If you recall back from physics, the kinetic energy of some body in motion is 1/2 m, and I'm going to write it here as u squared. In physics, you normally see it as 1/2 mv squared. The v is the velocity of the particle. But in chemistry books, for some reason, they usually use the letter u to represent the speed. So what this is telling you is the kinetic energy, or how much energy of motion a molecule has, is the number 1/2 times the mass of the molecule, right, in kilograms or whatever, times its speed in meters per second. Okay, now from physics you may have done this calculation many times. This equation applies to bowling balls. If I know the bowling ball is 5 kilograms and I know its speed, I'm rolling it with 2 meters per second, I square that guy, multiply by the mass, multiply by 0.5, and I get a number back, and that represents the energy of this guy. And when you measure and calculate energy, the units are what we call joules, which we just use the letter J to represent the units, okay? So basically this equation applies to bowling balls, but of course we're talking about gas molecules. So this is the kinetic energy of one molecule. If we knew the mass of one molecule, which we can calculate, we can look at that and figure that out, and we know how fast this molecule is going in meters per second, then we can calculate how many joules a single molecule has. Now you see, you start to get to the real problem with kinetic theory though. We can write this down, which means that every molecule, we can know each molecule's velocity, right? And we can calculate each molecule's energy, right? And we've been talking about that. But the problem is there's billions and billions and billions of molecules. There's no way that you could ever possibly know what each of their speeds are. It's just impossible. There's just too many of them. You might be able to measure a few of them, but there's no way that you'd be able to measure all of them in a pressure vessel with billions and billions and billions of gas molecules. You just can't. So that's why I say the detailed math of kinetic theory really goes into the realm of statistics. You start looking at how the large-scale behavior of lots of different things are. Okay? So, for instance, we can, if we wanted to go and start to take a statistical way of looking at this, this is how a single gas molecule may behave, but we can also define the average speed of the gas molecules. We can define that, okay? And the way we would define that is we would say, instead of u, we would define u bar, which means the average speed. How would we do that? How do you calculate the average of anything? You take molecule 1 and you add it to the speed of molecule 2, and you add it to the speed of molecule 3, right? These are all different molecules. And then you have, I don't know, 16 billion more molecules to add up. So we have capital N number of them. So you add all of them up. It's like averaging grades, right? And then you divide by capital N. So to find the average speed of gas molecules, if you know molecule number 1 is 2 meters per second, molecule number 2 is 1.5 meters per second, molecule 3 is 4 meters per second, add 16 billion of them up, or however many you have, get a giant number on the top, divide by however many molecules you have, and then you have calculated what we call an average speed of these gas molecules. But again, even though we can write this down, it's still cumbersome, because ultimately we're never going to be able to figure out what everybody's speed is. So we'll never be able to calculate truly what the average speed of the molecules actually are, okay? But what we can do is just continue along this path of saying, well, what if we could, okay? What if we could write this down? How would we find the average kinetic energy? Because remember, we're saying that the average kinetic energy of the molecules is proportional to the temperature. So ultimately, we want to write down what the average kinetic energy is. So we can write the average kinetic energy of the molecules. Molecules, okay? We can write the average kinetic energy of the molecules as follows. Even though it's not practical, even though we may not be able to actually plug it in, we can still write it down. Average kinetic energy, like this, is equal to what? Well, we said the kinetic energy of a single molecule is 1/2 times its mass times its velocity squared. So we can say the average is 1/2 times the mass of each molecule, because don't forget, each molecule has the same mass, right? Same mass. Times, now here's where we got to talk very, very specifically. U squared, and we'll take the bar and put it on top of that. What this is basically saying, this is quite different than this. I just mostly wrote this here for you to understand how you might calculate the average molecular speed. You add them all up and you divide by n. But when we're finding the average kinetic energy, we really do not want to use this. What we really want to do is we want to add up all of the squares, right? And then we want to calculate the average by dividing by the number of molecules. So if we knew everybody's speed, then we could square everybody's speed, and we could find the average by adding up everybody's squared speed and dividing by the number of molecules. That would give me what I call the mean of the square of the speeds. And if we have that number times the mass, because all of them have the same mass, times 1/2, this would give us an average, because this is an average. And this will be the average kinetic energy, which we're already saying is proportional to the temperature. So you see what we're trying to do? We're trying to go zoom into the molecules. We're trying to figure out what the kinetic energy of these molecules might look like on average. And then we're going to tie it back to something macroscopic, like the temperature. And that's how we bridge the gap between the microscopic and the macroscopic, is by zooming in, looking at these kinetic energy equations, and then zooming out and looking at something like temperature. All right, but I really want to drive home to you that this thing is not the same as this. This is the average of the speed of the gas molecules, right? This thing is called, let me make sure I catch myself on here. This is called the mean squared speed. And the way you would calculate this, if you could, is you would do the following. U squared bar. It would be U1 squared plus U2 squared plus U3 squared plus ... U16 billion squared, however many you have, and you would divide by capital N, the number of molecules you have. So you see what you're doing is you're taking the squares of each individual molecule of their speeds, you're adding them up, you're dividing by n. This gives you an average of the squares of the speed. Why do you want to calculate the average of the squares of the speed? Because kinetic energy is not related to the velocity. It's related to the velocity squared. So if we want to find an average kinetic energy, we need to find the average of the squares of the velocity. So we find the average of the squares of the velocity. That's what this thing is. We multiply by the mass, because the mass is the same for each molecule, and then by 1/2. This is a representative average of the squares of the speed of everything that we have in our tank, times 1/2 times m. This guy gives us the average kinetic energy of all of the gases in the tank, basically. But again, it's not practical. You can't really find this number. At least you can't do it by experiment, okay? But still, we can write down what we think it would be if we could do that. So we're rapidly approaching the punchline. We have found an expression for the average kinetic energy of the molecules in a gas. It's related to something called the mean of the squares of the speeds, okay? But we already said that the average of the kinetic energy is proportional to the temperature, okay? So we can basically look at this guy and bring those two ideas together. We can say that we know that the average kinetic energy is proportional to the temperature, right? Then notice this constant of proportionality. If we want to remove that, we can then say that the kinetic energy is then equal, not proportional, equal to the temperature times some constant of proportionality, right? So this is just a constant of proportionality. This is exactly what we've done many, many times before in Charles's law, Boyle's law, and so on. We've written down proportionality, and then we've taken the proportionality out, put an equal sign, and we stick a constant over there, and then we can rearrange. All that we're saying is that as temperature goes up, kinetic energy goes up. As temperature goes down, kinetic energy of the gas goes down. Or more appropriately, really, as the average kinetic energy of the gas increases, it implies in a higher temperature. The constant of proportionality is just here because these guys are not equal to one another. It just means that as one goes up, the other one also goes up. There still has to be some constant of proportionality in here. And if you remember, the ideal gas constant, or the universal gas constant R, came about as one of those constants of proportionality. So we spent this whole time talking about how kinetic energy works at the molecular level, and now we've taken that idea and we have said that it's equal to some constant times temperature. And I'm telling you as fact that the temperature is proportional to the average kinetic energy. You have to take that as faith, on the part of the scientists that developed this. It's not something that you would just sit on a Saturday afternoon and say, yeah, that's true. It's something that they made an assumption, they did the calculations, they developed this theory, and lo and behold, this theory does agree with every other law we have, the ideal gas law, right? So moving along, basically, since we say that this is true then we can substitute in what we know from this, 1/2 times the mass of the molecule times the mean of the squares, this is the average kinetic energy, is then equal to some constant of proportionality times the temperature, right? Some constant of proportionality times the temperature. So where we're going with this is, when we study kinetic molecular theory, we want to develop a equation that would allow us to calculate, on average, the speed of the particles of the gas, right? But as we know, there's different ways to define the average. We had one way of here, but then we figured out that this is a whole lot more useful because the velocity squared is related to energy, and energy is related to temperature. So this is a much more useful quantity than this thing when we're discussing how energy and temperature are related to one another. But the end game here, the end game of kinetic theory for the purpose of chemistry, is really just trying to figure out, other than the general concepts, how do we calculate a value for the average of the squares of the velocities here of the gas particles. So let's do some rearranging here. U squared, the mean of the squares of the velocities, would be equal to, if we multiply by 2, this would be 2 times c times t over m, little m. This is the mass of an individual particle, right? All I did was multiply by 2 on both sides and then divide by m on both sides. But notice that this is the mean of the squares of the particles. So if for some reason we knew what this constant was, and we knew what the temperature was, and we knew what the gas molecular mass was, we could put everything in here and we could figure out an average for the squares of the speed. But I just told you a second ago, we want to calculate a representative value for the average speed of a single gas molecule. So we don't want the average of the squares. We want to take we want to take the square root of this guy, and we call that URMS. And I'll explain why we call it RMS in just a second. But basically, if we take the square root of both sides, that'll be the square root of U squared bar, and then we take the square root of the other side, 2ct over m. Okay? Okay, so what we have here is what we call RMS. This means root mean square. Okay, and the reason why it's written like that is because it's very descriptive of what it is. We take the square root of the mean of the squares of the speed. Remember, I kept calling this is the mean squared speed. It's very descriptive. We're taking the mean of the squares of all of the speeds of everything. If we take the square root of that guy, we get the square root of the mean of the squares of the speed. Then this number here, URMS, is kind of a representative value for the speed, the molecular speed of a gas molecule. That's what we really want to know. We want to know how many meters per second on average is one of these gas molecules actually traveling at a certain temperature. Now this particular equation is not too useful because you have a 2 here, you have a t, you have an m, but you have this unknown constant c. Now here is where I'm going to wave a magic wand, and I'm going to tell you that RMS is the square root of U squared bar. This is the root mean squared. And really, you can go from this to the following. 3 times the universal gas constant R times the temperature in Kelvin over not little m, big M. This is the molar mass. Okay, this is the equation that you would use to actually find the RMS speed. I just did all of this stuff to get you to this point to see that there's very strong similarities. You see, what you have is a number. Yes, I realize that 3 is different than 2, but keep in mind that this is a number, okay? Here is a constant, here is a constant, here is a temperature, here is a temperature, here is the individual mass of a single particle. This is the molar mass, right, that we use from the periodic table, all right? And so you can see that even though they're not exactly the same, they have very strong similarities, and you take the square root of the whole thing, right? Getting from here to here is not something I'm going to prove for you because it's just beyond the scope of what we want to do here, but it is very possible to go from here to here, and this is what you're going to use for the to calculate the RMS speed of a gas molecule. Now, what does that mean? That means that if I know the molar mass of a gas molecule, or a molar mass of a gas, and I know its temperature, and of course I know the universal gas constant, and I know the number 3, right? I can multiply, divide, take the square root, and I'm going to get a number back in meters per second. And that's going to be kind of the representative value for the velocity of an individual gas particles. Of course, some of the molecules are going to be going faster than that, and some of the molecules are going to be going slower than that. But this is a representative value of the root mean squared. So it's very similar to the average speed. It's not exactly the same number as the average speed, but it's very, very close. And it's more useful to use a root mean squared like this because root mean squared is related to the energy, which is related to the temperature. That's why it's useful. That's why we don't use this other definition up here, because we end up wanting to know the squares of the speed to calculate the energies. It all goes into the detailed math behind the scenes of all of this stuff. Now I need to write a couple of very, very, very important notes to use this equation. So you have to do this or you're going to get the wrong answer every time. R, you must use the value 8.31451, and that's units of joules, moles, Kelvin. All right. Notice the unit of joules here. That makes a whole lot of sense because we're talking about energy, right? So that's the way it's derived here. Of course, they could have derived another value here or another form of the equation that you would use a different version of R, but to get it into such a nice, pretty form, the nice people that developed the theory use this value of the gas constant. The second thing is the molar mass here, M, usually when we're talking in the periodic table, it's grams per mole. Grams per mole, that's what we always say, grams per mole off the periodic table. But whenever you use the molar mass in here, you need to use the units of kilograms per mole. Kilograms per mole. So you do not look at the periodic table and say 16 grams per mole and stick it in there. You got to convert it to kilograms per mole, which is very simple. You just move the decimal point. That's all you have to do, but you have to do it. Now you ask yourself, why do you have to do that? Well, because ultimately this is a fundamental equation of physics, right? So it's dealing in units of energy. And so you really want to use the fundamental units, the fundamental SI units. If you think about it for a second, grams is not a fundamental SI unit. Kilograms is really the base unit in the SI system, right? And so you want to use kilograms per mole in here. That's how the thing is derived. And then the gas constant, of course, we already talked about. You want to use the one that involves joules because the way to remember it anyway is that we're dealing with energy here. That, believe it or not, is all I want to say in this lesson. I know that there's a very big leap of faith going from here to here. I do not expect you to totally understand that, but you should still see that the important thing here is that as you increase the gas temperature, the average, the RMS speed, which is kind of a representative speed of the molecules in the gas, it goes up, right? And the other important thing here is if you increase the mass of the molecule, which is the same as increasing the molar mass, right? If you make a heavier and heavier and heavier gas, if you take everything else constant, heavier gases move slower because bigger M's drive this whole fraction down, even after a square root goes down, so you have slower moving gases. So the way to get the fastest gases possible is to have really, really lightweight gases to make this very, very low and to have very high temperatures. If you have a high denominator and a high numerator and a low denominator, that's going to make for a very, very fast gas. Okay, and we'll do some examples to show how that works. So if you have very heavy gases at the same temperatures, they're going to be moving slower. That is the general idea of the kinetic molecular theory. Gases are a collection of molecules. They're really small. Molecules of gases are in continual rapid motion. Molecules collide often with each other and with the walls of the container. These collisions give rise to the concept of pressure. The average kinetic energy of the gas molecules is proportional related to the temperature of the gas. And the ideal gas law comes directly from kinetic theory, which we haven't proved here, but that is why we know it's self-consistent. And we can use the ideas of kinetic theory to define things like average speed and mean squared speed. And when we relate the energy of the particles back to the temperature, we can figure out that the root mean squared, which is a representative value of the speed of the particles of the gas, okay, takes this form. You can then use simplification to take this and beat it into this form, which is very, very, very useful because you can find the molar mass of anything on the periodic table. Just make sure and use kilograms per mole. And you can put the temperature in Kelvin, use the proper value. You can find the speed of any gas you want, basically. So that's all we want to talk about here. Follow me on to the next lesson. We'll finally put some numbers to it, and you'll see how to use these equations when you're solving real problems.